Hey, this is a lecture about annuities and the future value of annuities. Hey, who wrote all this stuff on the board? I did. I wrote all that stuff before I started the video to save us a little time here. So pause the video if you need to go through it a little bit slower. Okay, so what's an annuity? Have you ever heard of that before? If you're somebody who's saving for retirement, you may be doing that by adding a little bit of money every week or month or so forth into an account in the hopes that later you'll have a giant nest egg of money that you can then use throughout your retirement. Okay, so an annuity is basically a long-term savings plan, and the characterization is that it has regular fixed deposits of the same amount every single time. Okay, so I'm going to deposit money on a regular basis, and it's going to be the same amount of money every time I deposit it. Then the other thing is that the holding place for my money, whatever the account is that the money's stored in, is going to work on compound interest, which we've discussed quite a bit in the previous videos. And this start thing is very important here. The number of deposits per year that you're making must be equal to the number of compounding periods per year. Okay, so that's to say that if this is working on compound interest and it's compounding monthly, then my deposits will be made monthly. If my compounding is happening quarterly, then my deposits must be made quarterly, weekly with weekly, etc. The number of times you put in money has to be the same as the number of compounding periods per year in order for the math to work out as easily as we'll see it here. One thing that you may have realized, though, is that out of all the types of compound interest that we've discussed, the best one really was called continuous compounding, at which your money is compounded continuously every second of every minute of every day. But it would be impossible for me to put a tiny, itsy bitsy, infinitesimally small amount of money into my account every single minute of every day. So therefore, we cannot use continuous compounding. We are going to be using compound interest and the general compound interest formula here, which is to say not continuous compounding. Okay? So what I wrote on the other board here is that there's two main types of annuities that we're going to be discussing. Both of them have those fixed deposits happening periodically. But if it's called an ordinary annuity, that means that each of those deposits is going to be made at the end of the compounding period. Okay, so let's pretend we have a bank that's offering us monthly compounding at a fixed annual percentage rate. That means if it was an ordinary annuity, I would be depositing my money at the end of every month. And that's as opposed to the other type of annuity called annuity due. It's a little bit weird of a name. And in annuity due, it means that the deposit is made at the beginning of the compounding period. Okay, so once again, if my bank was offering an account with a fixed APR at monthly compounding, an ordinary annuity would have me putting the money in at the end of every month. An annuity due would have me putting the money in at the beginning of every month. That's the only difference, and you're going to see a slight difference in the future value equations that I'm going to present next. Okay? So now I'll erase all this and replace it with my favorite thing, which is a bunch of math. And I'll give you the two equations that will determine the future value of annuity given those fixed payments. Let's first define our variables here, okay? And these are going to be the same variables for ordinary annuity and annuity due. S, as we've always worked with it, is what we're going to denote for our future value. R, that's going to be the amount of each fixed deposit, okay? So if it was monthly, that's how much money I'm putting in every month, etc. That's the amount of each fixed deposit. N is going to be the total number of compounding periods, or the total number of payments, really. Okay, so total number of payments is the same as number of periods that's compounded over. And actually from before, if you guys remember in the equation that we worked for before for general compound interest, we had the same letter N, and it was the same thing as multiplying M times T, where M is going to be the amount of compounding times per year. Okay, and then another thing that you saw in the general compounding formula was I, and that's what we refer to as the periodic interest rate. Okay, I introduced that in a previous video called General Compounding, and in that video you saw the definition of I as the rate R. This is the APR as a decimal divided by M. Okay, so go back to the video on General Compounding if you're not familiar with the N and the I. The N is the same thing as M times T. The I is the same thing as R over M, where the R and the T are defined as previously, and the M was the number of compounding periods per year. Okay, that was from the previous video. And S is always future value, and R, before we were talking about principal, so you can kind of think about that as a mini principal, but it's not a principal. R is not a principal because that's an amount of money in a regular deposit. So I suppose you could think of the letter R as standing for regular because I'm regularly depositing a fixed amount of money over and over and over again because I'm slowly building my nest egg. Okay, so that's the difference. Now I'll give you the future value equation for ordinary versus annuity due. Okay, and they're quite similar. In the ordinary case, the future values are times 1 plus I raised to the n minus 1 divided by I. Okay, and then in the other case, I have the equation that S is equal to R times 1 plus I raised to the n minus 1 divided by I, same as before, then multiplied by an extra term right there times 1 plus I. Okay, so let's look at these two equations right next to each other. They're both outputting the future value, and the inputs that you need to give here is R, the amount of the regular payments, 1 plus I, remember I is the periodic interest rate. So I is going to be the APR R divided by the number of compounding periods per year M. And then you see that familiar 1 plus format that was also in the other equation there, in the other general compounding equation. Then it's raised to the n, and keep in mind that this n here is not exactly time, but it's the number of payments, same as the number of periods, and it's the amount of time in years multiplied by m, the number of compounding periods per year. So you can think of this n as same in the general compound interest formula, the total number of compounding periods over the lifetime of the annuity. Okay, so that quantity, subtract 1 from that, divide the whole thing just by I, not 1 plus I, but just by I, and then you will output the future value of an ordinary annuity. If you happen to have an annuity due where you're putting in your deposits at the beginning of each period as opposed to at the end of each period, the only difference, you see the same exact bracketed fraction here, is that you have this little extra bit where you're going to multiply by 1 plus I, and you can see 1 plus I is actually the base that I'm raising to n, the number of compounding periods here. You can just think about that for a minute. An annuity due says that I put the money in at the beginning of the period. If you want to think about monthly, let's say at the beginning of the month I put in my money versus at the end of the month I put in my money. Okay, so what happens in an annuity due is that you accrue just a little bit extra interest. You accrue the 1 month extra of interest because you put it in at the beginning of the month as opposed to waiting till the end of the month. And that little bit of extra is represented by multiplying that whole thing by 1 plus I. Okay, so let's see how these work. Let's put this into action with some questions that are going to ask you for future values. I'll also show you how to do it backwards. I'll show you how to do solving for time problems and mix it in with a little general compound interest problems. Okay? So for my first example, let's call her Mary. She's going to put in $500 at the end of each month. Okay. Into an account with 3% annual percentage yield, 3% APR, and that APR is going to be compounded monthly. And note that Mary's putting in her money one time at the end of each month, and so she has to be putting it into an account that's getting compounded monthly because the compounding rate has to match the rate at which you're entering your payments. And how long is that happening? She's going to do that for 15 years. Okay, so the question is, what is the future value of her account? What's the future value? This type of question isn't so bad, but some of the challenges you're going to face are making sure that you take the annual percentage rate R and turning it into I, the periodic rate. Keep in mind that I is equal to R divided by M. Okay, and the other thing you got to watch out for is that you got to transfer time. Here we have time is 15 years. The N that you're raising it to is not just the 15 years, but it's MT. So it's like 12 times per year times the 15 years, okay? So watch out for those two things, and keep in mind the definitions of the two types of annuity. The ordinary one is money goes in at the end of the period, and the due is the money in at the beginning. And that's the difference, okay? So the money goes in at the end versus money goes in at the beginning. So my first question to you is, which equation are we using? Is this an ordinary annuity or an annuity due? Put it in at the end of each month, okay? And that's the keyword you're looking for right there to say that that's an ordinary annuity. Ordinary. Okay? So we're going to use the ordinary annuity equation because we saw the keyword at the end of each month. Okay, and now don't forget we have to get the I here. The I is going to be the 3% written as a decimal divided by the number of compounding periods per year. And then you have to look for another keyword, the word monthly that appears here and also right here tells us that the M is equal to 12. So the periodic interest rate here is 0.03 divided by 12. It looks like we're also going to need the letter R. What's the value for the letter R? That's the regular payment. That's right. So you're going to have $500 for the R. And then the last letter we need is the N. And that's going to be 12 times a year times 15 years total. Okay? So I'm going to just leave up the ordinary one because that's the one we're using right here. And I'm going to show you how I've plugged in each of the values. Maybe the other sticking point on a problem like this for you is going to be able to just crunch this all into your calculator and make sure that you output it exactly to the nearest cent, okay? So taking it from over there, S is equal to 500 times the quantity 1 plus I. Let's see if this one comes out to be a fixed decimal. This is 0025. That's really nice, okay? If your I, after you divide your annual rate by the periods, compounding periods, if you get a decimal that's not repeating, that doesn't go on forever, then feel free to take that and you can just add it to one right here, make it a little bit simpler for yourself, just like that. Okay, if you get a repeating decimal like 0.00833333, something like that, then you cannot do that. And I highly recommend for you, in that case of a repeating decimal, to leave it as a fraction and do not approximate it by a decimal because the round-off error is going to be huge. It's a major round-off error because you're raising this to the nth power, and here 12 times 15, that's 180. Notice this. I'm raising that base to the 180th power. If I have a little bit of round-off error in there, it is going to get exponentially exacerbated. I do not want that in my equation. I don't want that round-off error. Okay, so lucky for me, that one rounded off well, and the I goes on the bottom there. Okay, so on your calculator, you're doing like 500 times this entire quantity. You might want to put this entire quantity up here in brackets and then divided by the quantity on the bottom. And definitely encourage you to check this yourself. What number did I get from this? How much money did Mary accrue over that 15 years? $113,000. Yeah, nice. That's a pretty nice nest egg for Mary. Okay, so you can see how all that hard work of putting in $500 every month, that's nothing to sneeze at. That's a lot of money per month. But if you keep putting that money in once a month for 15 years, bam, you're going to have a ton of money at the end. That's really nice. Okay, let's try it again. And I definitely want you to be hands-on with this as usual and try to do each one of these yourself. Don't just assume that you're going to be able to crunch that out and it's going to go fine. Make sure that with your personal calculator and your own set of skills, make sure that you're ready to get all those numbers to exactly the nearest cent. Okay, so let's do another one. We'll call this guy Bob. Let's say Bob puts $1,200 into an account. Okay, and he does that not at the end but the beginning of each quarter. Okay, and let's say that the APR on that is at 4% APR, and he does that for 10 years. And the question once again is, what's the future value of Bob's money? He's going to put in $1,200 at the beginning of each quarter. Now $1,200 sounds like a lot, but do you guys know what I mean by quarter? That means quarter of a year, okay? So the keyword quarter right here means I only have to do this 4 times a year, or once every 3 months. If it says once every 3 months, that's the same thing as quarterly compounding. So dividing that by 4, that's only $300 a month. That's actually less than Mary's doing, okay? And again, the question is, what's the future value? So we're going to have to see what kind of equation we need. What type of annuity is this? And where's the keyword for that? Right, it says it right here at the beginning of each month, so that means that it's an annuity due. Okay, so I'm going to change this over to just say I need to use my annuity due equation. Okay, so remember, the only difference between an ordinary annuity and an annuity due is the addition of this little multiplicative term right here, 1 plus I. Okay, so now it's the future value of an annuity due, ordinary due. Ordinary due. Okay. So just recognize that from the words. It says at the beginning, so I have to use due. There's that one. And then here we have the R as 0.04. Here we have the T as 10 years. But once again, look very carefully at that equation and make sure you understand what those variables mean individually. It asks you not for R, but for the I, which is going to be R divided by M. Okay, and so the I is going to be 0.01. It doesn't ask you for the T. There's no T over there, but there is an N. And the N is M times T, and that's 4 times a year, times 10 years altogether. And so that's 40 total times that he's put in that money. Okay, so you might want to do those ones over on the side just to make sure that you remember. Don't just blindly plug in the R and the T, or else you'll mess it up. And then you just plug them all into the equation. Actually, I forgot one thing. Do you guys remember it? What's the R? Okay, so what's the value for R in this one? That's the regular payment amount of $1,200, that's right. And now on this board I've set up every single letter with a mathematical representation of the number, and so I have to just replace the numbers where I see the letters in the equation, and that's going to be 1.01 raised up to the 40th power minus 1, and then I'm going to subtract 0.01. And don't forget, because this is an annuity due, I have to multiply the entire thing by 1.01. That's because I was getting just 1 extra quarter's worth of interest on each one when I'm doing it as an annuity due. Okay, so once again, I really want you to try to plug that into your calculator. Don't wait till it's too late. Make sure you can do these ones before we start asking you ones that are even harder. And make sure that you get that money. Get that money. It's $59,250.28. Good job, Bob. So that's a lot of money that Bob has saved in his account. But another question that I might ask actually is how much interest did Bob earn? Okay, when you really think about like the amount of money that he put in $1,200 and he put that in 40 times. Right? And then he got 59,000 some odd money out. How much money did he actually put in? How much interest did he earn? Okay, so let's answer that question on this board over here. Try to figure it out. In case I would say how much interest did this annuity accrue? Or did this annuity earn? Okay, and remember that the interest, well, actually, this isn't really principal, but the concept of interest is that you take the output money and then you subtract off how much money you actually put in. Okay, so I got out the 59 to 50 and 28 cents, but how much money did Bob actually put in? He had to put in $1,200 40 times. Okay, so what's 1,200 times 40? That's going to be $48,000, but he got out $59,000. So actually the interest that he made here, the amount of interest he made, is the difference, which is $11,250.28. Sweet, $11,000 worth of interest. An annuity is a good idea. Saving for your retirement is a very, very good idea. Okay, so maybe you don't have enough money to be putting in a big fat $12,000 every 3 months. Let's say you're going to go small, but you still want to save. Let's say we got another guy over here called Jake. He's just going to put in $1 a day. That's all he can afford, but it's better than nothing. So let's see what happens to Jake if Jake puts in $1, and let's say it's at the end of each day. So Jake puts in $1 into some account, which is open 7 days a week at midnight, by the way, at the end of each day. And the money is accruing at 2.5% APR. And remember that, how is the account going to be compounded? It has to be compounded daily because he's putting it in every day, okay? So that has to match because both of those things are conceptually linked to the value of the letter M, okay? And then how long is he going to do that? Oh, you could probably do that for a while. Let's say he does that for 30 years, okay? So just $1 a day for 30 years, what kind of nest egg could Jake expect out of all those dollars adding up? Once again, we have to figure out, very first and foremost, which equation are we using? Which equation are you going to use? Ordinary annuity or annuity due? That's right, at the end, okay, end of each, that's the key word, and so that says it's going to be ordinary. Ordinary. Okay, so I'll put up the future value equation for an ordinary annuity right here, 1 plus I to the n minus 1 over I. Okay, and then after we get that, we have to get all the letters. We have to get the I, the N, the R, and secretly, even though the M is not there, that all has to do with figuring out the M. What is the value for the letter M? Compounded daily. So that's the key word that tells you the number of compounding periods per year, M, is 365. Okay, and then you can start to extract the I, because that's going to be the annual interest rate as a decimal divided by 365. Now that looks like something that's not going to come out pretty. If I actually try to divide it and see what the decimal for that is, it's going to be something repeating with a long list of numbers. So I'm going to leave that as a fraction when I do the calculation. Okay, the other thing is the N, and that's going to be 365 times a year for 30 years, and that's going to be a huge number, whatever that's going to be. And then the R, what's the value for R? Oh yeah, that's just the $1. So that's actually just going to be equal to 1, because it's just doing $1 a day. So we put that $1 in, and then we have to do 1 plus 0.025 divided by 365. Keep in mind when you're entering this on your calculator, 1 plus this fraction, okay? You're not dividing the 1 by 365. You're just dividing the APR by 365 and adding 1. So watch out for that. Make sure you do that properly. And then you have to raise that to the quantity 365 times 30. Whatever that giant number is, that's the number of dollars he actually threw in. So you're going to raise it to that, subtract off 1 for that whole thing, and divide by 0.25 over 365. Okay, so if you've been checking your work so far, hopefully you're getting more and more comfortable with actually crunching out all the numbers in the previous examples. And this one is just one extra step a little bit harder because I'm not changing this fraction into a decimal because it's probably repeating or it's just really ugly looking. Okay, so go ahead, plug that in your calculator, make sure you're going to get the same amount as I do. How much did he get? 16,307 and 41 cents. Oh, that's actually not as much as the other people got. So I guess you probably do have to save a little more than $1 a day to be able to live off that $16,000. Okay, let's try to answer the interest equation though. You notice the last person made quite a bit of money off interest. So let's try to answer that question for Jake too. How much interest was earned on this? Okay, how much interest? Try to answer that question before I write it down. Pause the video and then try to calculate how many dollars did he put in. And he came out with $16,307.41. How much interest did he make? Okay, and the answer to that is going to be the future value, the amount he came out with. And you're going to subtract off the amount of money that you put in, which is 365 days times 30 years. And then it was just $1 a day. And so this number here, let's see, 365 times 30, this was $10,950. So he actually put in less than $11,000. He put in $10,950, but he came out with more than $16,000. So the amount of interest he earned was $5,357.41, and that's just an interest. And that is very interesting, isn't it? Because actually he didn't even put in that much money. Notice he put in about 10 grand and he got 5 grand in interest. So 50% of the money he put in himself was actually just thrown in by the bank just in the interest. And look at this interest rate. It's only 2.5%. So it's not because this was a ludicrously high interest rate. The reason that he made so much money proportional to how much he put in interest is because he did it for so long. Okay, so now it's time for Dr. Navala's tips for life. Start investing in your retirement now. Start saving now, because if you start saving when you're young, even if you just put in $1 a day, the longer you let it sit in the account, remember, this is an exponential model. It grows exponentially. The longer you let it sit in, the more interest that you're going to get. Okay, so don't wait until you're 50 to start saving for retirement at 70. If you actually start when you're 20, you're going to make so much more money off that exponentially growing model if you let the money sit in there for a longer time. Okay, am I taking my own advice? It's none of your business. Okay. Let's try some other questions here, like, I've done a lot of future value. What if I want a goal? I have a goal for my future value, and I want to know how much money I have to put in each payment period. Okay, that would involve solving for the payment amounts. So let's try a little bit of that. Let's find payment amounts, or payment, or aka deposit. I think I was calling it deposit earlier, but payment, same kind of concept there. Amounts to reach a goal for your future value. Okay, so for example, actually before I do the examples, these are going to be examples where my known variable is S, the goal that I have in mind is known, and my R variable, the amount of each payment, is unknown, because I'm trying to feel out how much I have to use in order to get a certain amount out. Okay? Well, guess what? I can actually make this go a little bit faster if I take the future value equation, and I'll just do this for the ordinary annuity, but you could also do this for annuity due in the same way. Take this equation and backwards solve it for the R, which is to say, put the R on the other side and solve for it, okay? So let's say, if I wanted to put the R on this side, I would have to divide both sides of the equation by this ginormous fraction. What does it mean to divide both sides of an equation by a fraction? That's the same thing as multiplying by the reciprocal of the fraction. So therefore, if I wanted to solve for the R would equal S, multiplied by the reciprocal, or if you like, the upside down, of the fraction. Okay, so this one is solved for R. It's the same exact equation, but instead of being solved for S, now it's solved for R, and that's really going to help me when it's time to figure out a question of, let's say I have a certain goal of money I want in my nest egg account. How much do I have to put in if I know how long I'm going to have to do that for? And the requirements of the account, etc. Let's do an example right here. Let's say I want to have $40,000 in 12 years. and I have an account that gets 3.5% APR, and that's going to be compounded monthly. Okay? The question is, how much money do I have to put in each month? How much money do I need to deposit per month? Deposit per month. Okay. Now, why would I ever need $40,000 in 12 years? That sounds silly. Unless maybe you have like a 6-year-old at home right now and you know that when they turn 18, college is going to cost a lot of money. College is not cheap. So let's say that that's my goal because I'm trying to save for my child's education fund. And I want to start putting in money, but I wonder how much money would I really have to put in if this is the offer that the bank is giving me and I want to have $40,000 to be able to just hand over to that kid to go to college in another 12 years. Now that makes it a good question, okay? So one thing I have to say is that there's a name for questions like these. If you need to know the payment amount to reach a goal because you have to pay a giant bill sometime in the future, this is also known as a sinking fund. Okay, so I'm just going to put this up here and say AKA sinking fund. Okay, and once again, that is like a sinking fund is like when you have to pay off something and you're going to pay it off in just one giant lump sum and you wonder how much should I be saving incrementally, bit by bit, so that in a certain number of years I can just hand over that large amount of money. So maybe it's sinking because you're going to be kind of sad to have to hand that over, but that's why they call it a sinking fund, I guess. I don't know. Anyway, let's answer the question, and I'm going to go ahead and answer the question using the equation right over here that I already solved for R. Now, it's not necessary for you to do that, and this is not a separate equation. This wouldn't be given to you if I was your teacher and I was giving you a test. I would only give you the one equation. I would expect you to be able to algebraically manipulate the equation to be solved for either S or R, whichever one you want. Okay? But since I already took the time to multiply by the reciprocal on both sides and solve this out for R, I'm going to just use that to my advantage, and I'm going to plug in S. Notice here that this is the output amount of money. So that's going to be the S. That's going to be $40,000. Okay, now it says I need I. Oh yeah, that's going to be the APR divided by the number of compounding periods per year. That's the I. Then I'm going to divide that by 1 plus that same exact I. And I'm going to raise that to the N. What is the N? Oh yeah, that's the total number of times I have to make that payment, which is going to be M times T. So 12 times 12 up there, 144. Minus 1, just finished copying that. Okay, there you go. There's my recipe right there, and then I just have to plug and chug, and I can't stress that enough that you should practice that on your calculator so that you know you'll be able to get that right number out of it. The number I got, oh, that's not so bad. Did you get that number? $223.91. That's manageable, okay? So I guess, kid, I'll be canceling cable so I can pay for your college in 12 years. Okay, so that's not so bad, but that's a really good thing to know how to do. All right, so let's do another one like that, and I'll leave that up on the board over there because we might have to use this again. Let's say... Okay, so let's do the sinking fund one. So before I said sinking fund over here, let me just reiterate what I meant by this. I'll call it a separate example. Sinking fund. A sinking fund is when you have to pay off a debt in one large sum. Pay off a debt in one large sum. Okay? And so along the way, knowing that you're going to have to hand over this giant chunk of cash someday, along the way you're going to save up bit by bit by creating an annuity for yourself and then have that amount of money ready to pay off the debt in one large sum. Okay, so let's say how much must be deposited at the beginning of each year to pay off $10,000 in 5 years. And then the account, I have to give you more information. Account is 7% APR compounded annually. Well, I guess that's the saving grace of this question here, is that at least I got a sweet APR of 7%. Again, email me if you ever find such a high rate on a savings account. So that's nice, and I have to pay up 10 grand in 5 years, which just back of the envelope kind of thinking, that's about $2,000 per year, right? This is compounded annually, and so am I thinking I'm going to have to deposit $2,000 each time? I don't know, something around that, just so I can think about it and hopefully make sense of my answer. Okay, now look at this work I did on the board over here, and I'm asking you right now, is this an appropriate equation for me to use on that question right there? Which money must be deposited? No, it's not. There's something more that I need. Did you guys catch what else I need? Why wouldn't this be good? What is this the equation for? This is the equation for an ordinary annuity. And actually that just reminds me, I'm not sure if I put on that last problem, but that last problem, the previous example, with the saving for college, I meant for the money to be deposited at the end of each month. Sorry about that, I don't think I wrote that on there, but in the last problem, the money was supposed to be deposited at the end of each month. And this one is purposefully contrasting that because it's deposited at the beginning of each payment period, so on annual compounding, the beginning of each year, and this tells me right here that it's not an ordinary annuity, it's an annuity due. Okay, so definitely need to have that written in each problem to be properly posed, and this one tells me I can't use the ordinary annuity, I have to use the annuity due. Dang it. Okay, so what's the equation for an annuity due? Let's change this around and make this for an annuity due. The only addition is putting a 1 plus I right there, right? Okay, so now I have the equation for annuity due, and same thing, since I'm going to be looking for R, I'm going to be trying to solve it for R. Can you guys follow along with where this extra term 1 plus I, where's that going to go when I'm solving it for R? It's multiplied by R right here, so it looks like it's going to have to be divided by right over there. Okay, cool. Now I have the equation solved for the amount of each payment when I have an annuity due. Now I can start to answer a question. I have an annuity due. How much must be deposited to pay off this amount and that? Okay, I need more board space, so let me just erase this part right here, and I'll use that equation that I've got. Now you can see over here we need the variables S, I, N. Can you guys write those down on your own page right now? Okay, so the S, that's going to be the amount we're going to have to pay off. This is a sinking fund, so we're just going to be handing that over at the end of 5 years. The I, that's going to be the interest rate written as a decimal divided by the compounding periods per year. How many compounding periods per year is it? Annually. Good. So I hope you recognize that, and that just means plug in M equals 1. Okay? So it actually turns out to be 07. And the number of times I have to do this, that's going to be the number of years times how many times per year. So because of the 1, it just turns out to be 5. Okay, cool. So then I have all the things I need, and then I can just start plugging them in right here. I'll put the 10 grand right there. The I, I'll put the 07. This, I'm going to put the 07. The N is going to be 5, and don't forget, this is an annuity due, so I have to do that little bit extra right there. Da-da-da-da. What did I get? 1625 and 15 cents. Okay, does this make sense? Is there any way I can tell? Keep in mind that sometimes, a lot of times, you can kind of do just an in-your-head calculation, and you should get an answer that is in line with that. Okay, so remember, I was thinking 10 grand, 5 years, how much per year? I got to do like $2,000 per year. But also, my money is growing. My money is accruing interest. So if I put in the first $2,000 in the first year, it's going to get like 5 years of interest because I put it in the beginning of that year. It's going to accrue 5 years of interest. So I should get an output here that is around $2,000, but it's less than $2,000. And that's what I got. So it makes sense. So that's a little bit of a check there. It's just the fact that it makes sense for me. Okay, and another way that you could possibly check it is keep in mind that this is a value for R. So if you want to take the original equation for the future value of an annuity due, and you plug this in for R, and that in for I, and that in for N, and then you output it to the future value, you should get a future value very close to $10,000. So that's another way to check your work. Okay, let's just go into the last question, which is going to be a doozy. This is going to be back to the solving for time issue, and you guys are going to need your logs, because remember, time is always in the exponent, okay, right here, the 5 years, always in the exponent. So whenever I do the solving for time, I'm going to need logs. Need the log, and what's my favorite log? ln. Right, so I'll give it an argument because it always needs an argument. Need to take the log of something, ln of x. Here's an example question. Let's say that I'm investing $800 at the end of each quarter. And that's at 6.2% annual percentage rate. And of course, that's got to be compounded quarterly because the compounding periods must match the deposit periods. How long is it going to take? How long does it take to be worth a grand total of, let's say, $20,000. Okay, so how long is it going to take if I put in $800 per quarter? Keep in mind that that's a 3-month period, a quarter of a year, and a 6.2% APR, but I really need that 20 grand. So how long am I going to have to do this so I can get the 20 grand? Where do I start? What kind of equation should I use? I've only got 2 equations in this lecture, that of an ordinary annuity's future value and an annuity due's future value. And which one is this? Keywords right here. End of each period, end of each quarter. So that means it's ordinary. I keep spelling it wrong. Ordinary. Okay. Beginning would have been annuity due. End, ordinary annuity. Let's write down the future value equation. 1 plus I to the n minus 1, divide that all by I, close it off. Okay, let's see, what are our knowns, what are our unknowns? Here it looks like our S is equal to $20,000. Our R, also known, $800. Okay, 1 plus I, what's my I? Let's see, well, it has something to do with this APR right here, right? But it has to be divided by something. What's it going to be divided by? Quarters. So that means m is equal to 4, right? So the I is going to be that divided by 4. So 1 plus 0.062 divided by 4. That quantity raised to the n. What's the n? N. That's going to be, I don't know. That's a question, isn't it? Because it's a question of how long. Remember that the n involves the time. The n is actually the total number of quarters. So I didn't ask how many years or how many quarters or how many days or whatever. So because the question is posed in terms of the unit, the time unit of quarters of a year, I will just solve it out for n, the unknown, the total number of quarters of a year. Okay? So that's my unknown. I don't know what that is. Put that over there. Put that right there. Yowza. This is a tricky one. This is a big honking equation right here that needs to be solved out for that unknown n. Okay, so let's see how good you guys are from solving those equations using the logs. What was step 1 in our strategy of solving logarithmic or exponential equations? isolate the term that involves the unknown. That's right. So we're going to want, number one, isolate the term 1 plus 062 to the 4 to the n term. We're going to isolate this term all by itself on one side of the equation because that's the term that has the unknown n up inside the exponent. Okay, so let's do this in steps. I'm going to do this real slow in steps. The first thing I'm going to do is divide this by 800, and that's going to be equal to all that stuff. By the way, is that a repeating decimal? Oh, sweet, there's one saving grace. That is not a repeating decimal, okay? So actually 1 plus 0.062 divided by 4, that is not a repeating decimal, so I can put it right there. But keep in mind, you can still do it even if it was a repeating decimal. To the n minus 1 divided by 0.3875. Huh, that doesn't look right, actually. Sorry, I rarely have to do this, but there's something wrong there. Because how could 0.062 divided by 4 be equal to 3875? That's just wrong. I can see that typo from a mile away. Okay, that's 0155, excuse me there. Okay, and then that's going to also be divided by 0155 on the bottom. Okay, and you might want to do this, you know, you could do this in a shorter amount of steps, but I'm just taking it really slow so everybody can follow along. And slow and steady usually does win the race, okay? So don't be shy if you want to be slow about this. Next step, in order to isolate this term, would be to multiply both sides by 0.0155, okay? So on this side, I'm going to get 20,000 over 800, and I'm going to multiply that by 0.0155. And then on the other side, I'm going to get 1.0155 raised to the n minus 1. Yeah, that looks pretty good. Okay, and then at this stage I would probably try to combine all these things together, and now I think I see where my typo came from, and I'll just do this on camera just to make sure I get it right. Divide that by 800. If I seek to simplify that, that's where I got my 3875, okay? So if this does turn out to be a non-repeating decimal, lucky day, because then you can just make it look a little neater. Okay, if it is a repeating decimal, you must continue to work the problem out, having a fraction in place. Okay, so then we got this to the n minus 1, and now I see why I had that 1.3875 is because at this stage I added 1 to both sides. Okay, so now you'll see me do that on the camera, plus 1 over here, plus 1 over there. So now I'm at this stage. Now if I asked you to solve this for n, you might say, okay, that's pretty reasonable. I know how to do that. In order to get the n out of the exponent, I'm going to take the natural log of both sides, just like so, and then the n will pop down, just like that. And then I'm going to get that n is equal to the ln of 1.3875 divided by the ln of 1.0155, and what I got for that was I got 21.2926 ... Okay, I solved it out. Now let me think about it for a minute so that I can properly answer the question. I got n equals 29.29, and the question was, how long is it going to take for me to hit a goal of $20,000? Okay, first of all, what does that mean? 29.29 what? Okay, answer. Try to answer that yourself. 21.29 what? Years? Weeks? Months? It was in quarters. So what that means is it's 29.29 quarters. Okay? Now keep in mind, an annuity is not a very flexible type of contract here. An annuity has a fixed payments that occur at fixed regular intervals of, in this case, quarters. Which is to say, after 21 quarters, I will not have $20,000. After 22 quarters, I will have $20,000. I'll have more than $20,000. But the thing is, there's no in between. There's no payment that you just throw in that's 0.29 of a quarter. That doesn't happen in an annuity. You have to wait until the next quarter and then input your payment. So I need 22 quarters. I always have to round it up. That's the thing that's for this type of question. Always have to round up here. And I don't mean that you always have to round up forever, because you've seen me round up and down and whatever. But in this case, in the case of the future value of an annuity, you have to round up because you can't make 0.29 of a quarter's payment. You can't call after 3 weeks and say, hey, can I just throw in a little more money? They don't do that. They only accept from you $800 exactly every 3 months. So you need to round it up. Even if it was 21.01, I would have to round it up because the question is how long until I get $20,000 or more. So here I need 22 quarters to get more, to have over, let's say, have over the line of the $20,000 goal. Okay, you will have more than $20,000 after the 22 quarters, but you did have to throw in that extra one to push it over your goal. So that's going to be my official answer, is 22 quarters, or if you like, or you could say 5.5 years, if you want to transfer that into years. But that is to answer the question of why I wouldn't just take this decimal approximation and divide it by 4 to get the number of years. I can't do that because an annuity is so rigid. You have to wait till that next quarter, round it up to the nearest whole quarter, and then if you like, you can transfer that into years. Alright, well, have fun playing with all these annuities, and don't forget to save for your own retirement.